Hello, we're Team 23067, and our project was to develop the renal extremity device to measure impedance, edema, and movement, or the Radium 2.0, for our sponsors, Dr. Slepian and Dr. Thatchian.
Chronic kidney disease is a leading cause of death in the United States and currently affects 1 in 7 U.S. adults. The kidneys play a key role in fluid balance regulation within the body, and dysregulation caused by kidney disease can lead to unwanted symptoms and comorbidities. These comorbidities commonly include excess swelling of the extremities, otherwise known as edema, and restless leg syndrome, which is a movement disorder that causes a deep discomfort within the legs that can only be relieved by movement. Right now, these conditions aren't able to be quantifiably measured because their presentation can be impacted by environmental conditions that can't be replicated in a doctor's office. Radium 2.0 is an at-home wearable device that allows physicians to collect and utilize this data to gather a more complete understanding of the disease progression at any given time. Restless leg syndrome is quantified by differentiating symptomatic movements from normal movements and tracking the frequency of the movements that are specifically due to restless leg syndrome. Edema is quantified by measuring the water content of the leg as well as the extent of swelling over time. This information is transmitted to a mobile application that displays the data in simple, easy-to-read graphs for physician interpretation to improve the standard of care provided in chronic kidney disease treatment.
As chronic kidney disease is an end-of-life condition, patient comfort has been a major consideration in our design choices. The Radium 2.0 device focuses on ensuring patients are able to engage in their day-to-day lives comfortably while providing their physician with the most accurate and up-to-date information.
As the device is worn throughout the day, physicians are able to get a comprehensive view of the patient experience and access data that assists in balancing medications and treatment methods. This allows for safer and more dynamic treatment that's tailored to the individual. With the ability to respond quickly to shifts in medication balance or treatment efficacy, patients no longer have to endure unnecessary exacerbation of symptoms until the next available office visit with their clinician, reducing overall discomfort and improving the quality of life for each patient.
In order to produce accurate results, the Radium 2.0 must be worn daily for a few hours. Since patients wear the device consistently, comfort is a priority. Radium 2.0 was specifically designed with a spandex material to allow for firm and breathable contact, Velcro for adjustable sizing, and a sock-like design to minimize sensor error. The microcontroller housing is placed on the outside of the lower leg to minimize its impact on the patient's daily life. With every aspect of the device designed ergonomically, the patient is more likely to wear the device.
Now we're going to go into how the subsystems actually work to make our system function. The first subsystem is our triaxial accelerometer that is used to capture the movements of the legs. Our next system is the EMG, which measures the voltage caused by the activation of the muscle. By measuring the activation of the muscles with the movements that were captured by the accelerometer, we're able to better differentiate between regular movements and the RLS movements. Our EMG circuit utilizes a differential amplifier and 6 op-amps to filter and rectify the signal. Our flex sensors are resistance-based and measure the curvature of the leg through a linear relationship between the bend in the sensor and the resistance recorded using a voltage divider. Finally, our bioimpedance system sends a low alternating current through the leg and measures the complex resistance. The lower the resistance, the greater the water content of the leg. It utilizes an impedance chip to generate a signal and then uses instrumentation amps and op-amps to filter it, rectify it, and amplify the signal.
In order to test the efficacy of our flex sensors, we developed a dry sponge drip system to simulate a patient's leg swelling over time. As the sponge was hydrated, the resistance of the flex sensors was recorded along with the change in volume of the sponge. After proving the flex sensors performed to our standards, the sensor system was then verified on volunteer test subjects. With the sensors sewn into the leg sleeve, a predictive model was developed by recording the resistance of the sensors and the leg volume. In order to verify the relationship between water loss and bioimpedance change, we developed a bioimpedance model using dough as a substitute for tissue. The dough was hydrated and weighed before being connected to our dry electrodes and dehydrated. At the end of the test, the dough was again weighed and the change in water content was determined by the weight loss through the test. By comparing the change in water content to the change in impedance, we were able to demonstrate that the loss of water resulted in an increase in impedance. EMG and accelerometry data was recorded on patients performing RLS motions, with regular motions being used as a control. Since RLS motion is involuntary, reflexes were induced and recorded through EMG for comparative analysis. This analysis allows us to differentiate voluntary and involuntary movements, as voluntary motion is lower in voltage amplitude when recorded by EMG. Involuntary RLS movements are also distinguished with our accelerometry data, because the intense motions result in higher acceleration values. By utilizing the two systems in conjunction, we can increase our detection accuracy.
The flex sensors that line our stocking were used to create a predictive model for edema that allows us to record resistance measurements over time and translate that data into a circumference value. Verification of our predictive model was performed by recording the resistance of the flex sensors during wear and comparing the calculated circumference to that of the actual leg. As the sleeve is worn throughout the day, the sensors will measure continuous resistance data, and a percent change in circumference is calculated from these measurements to track edema. Because there are multiple flex sensors, physicians can also determine where the swelling is most severe. This allows the physician to differentiate edema from natural swelling that may happen due to a patient being on their feet throughout the day. Edema is most commonly localized around the ankle, so a higher percentage increase around the ankle can indicate edema to be the specific cause of the swelling and guide physicians to adjust medication dosages and treatment methods based on the severity of the swelling recorded.
The results of the EMG and accelerometry testing allowed us to determine voltages and acceleration thresholds that can be used as markers for RLS motions. From this, a detection model was developed that successfully differentiated between RLS and regular movements.
Our impedance circuit was tested and confirmed using the DOE model as explained by William. Here we can see that over the course of one of our tests, the impedance increased by 20%, which correlated to a water loss of 0.7% of the mass of the DOE over the course of the test. This system was then verified on volunteer test subjects, allowing us to record bioimpedance values as the patient increased and decreased their water content over time. This fulfilled the requirements for accuracy within 95% and gathering the impedance data over time.
As chronic kidney disease is more commonly associated with an older demographic, we wanted to keep the app design simplistic in order to increase the ease of use. One of the key concepts we kept in mind for our project was to minimize the time it takes from the point when a user is downloading our application to the point when a user is actually recording data. That data that is recorded from our patients is stored in a cloud-based storage system called Firebase, so that we can protect the user's sensitive health information. Taking a look at the application, when users first download our app, this is the first screen that they will see. This is the registration screen as well as the sign-in screen, which are both standard features that you would see. After the user is signed in, they are brought to the main screen, where they can access the four main features of our application. The settings screen, where users can customize their profile, log out, etc. The connect your device screen, where users can connect the application to the REDM device through Bluetooth. The record and export data screen, where you can start recording the data as well as export your recorded data to your physician. And the view data screen.
Our final sleeve design houses all sleeve components and is available in different sizes, comfortable to wear for a long period of time, all while protecting the patient's anonymity.
Our ability to design and test models in a patient-focused manner has led to the device meeting all design requirements and being able to efficiently track the symptoms and comorbidities of chronic kidney disease. REDM 2.0 is now a complete and comprehensive system that is ready for use by clinicians and patients.